Alright, in this video we're going to talk about Unit 11 Objective 2, and this is going to be the first of several videos on Unit 11 Objective 2, and today we're going to talk about the integral test and the P-series test for convergence. Now in the last video we talked specifically about one type of series, and that was a geometric series. And those were pretty straightforward. We have a rule that can tell us if we converge and what we converge to if we can. But geometric series are only one type of series. It's one of the two that have a name, but there are a bunch of series that don't have a name. They're just infinite series, and there's a bunch of different ways that we can find out if they converge or not. And today we're going to talk about two different types, the integral test and the P-series test, to see if we converge. So the first one, the integral test, says if, we'll just say suppose instead of if, suppose f of x is a continuous positive decreasing function. So continuous positive decreasing function. So positive, continuous, decreasing on the interval some constant k to infinity. And let's also suppose that if we plug n in, we get some term in a series a sub n. Then, if the integral from k to infinity of f of x dx converges or diverges, then the sum from n equals k to infinity of an will converge or diverge. So if the integral converges, the sum converges. If the integral diverges, the sum diverges. Now, this is different from our geometric series in so much as this does not tell us what we converge to. And you'll actually see that all of our tests in Unit 11 Objective 2, they're not going to tell us what we converge to. They're just going to tell us if we converge. So the only test that's really going to tell us what we're going to converge to is that infinite geometric series. So let's take a look at an example, and then we'll talk about P-series. So we'll say, does the sum from n equals 2 to infinity of 1 over n natural log of n, oops, I wrote x, of n, converge? Now you can see that this isn't going to be a geometric series like the last one because we don't have some number to an exponent of n, right? We can't manipulate this to try to get r to the n power to see if we're going to converge or not. So we have to find a different way, and in this case we're going to try the integral test. So to do the integral test, we're just going to take the integral from, in this case, 2, because that's what our n equals starts at, our initial value of 2, to infinity of 1 over x natural log of x dx. Now to find this integral, we're going to have to do a couple of things. We have an improper integral because we're integrating to infinity, and we're also going to need a u. So let's go ahead and find our u first. So we'll say u equals the natural log of x, so du equals 1 over x dx. And if you notice, we have a 1 over x dx in our problem. So that's going to work out pretty nice. So we can now say the integral from the natural log of 2, changing our limits, to the natural log of infinity of 1 over u du. Now, if you think about what the graph of natural log looks like, it looks something like that. Natural log of infinity is just going to be infinity. So let's rewrite this as the integral from the natural log of 2 to infinity of 1 over u du. Now, since we have an upper limit of infinity, we need to think about our improper integral. So that's when we end up taking the limit as some variable, we'll call it b, goes to infinity, of the integral from the natural log of 2 to b of 1 over u du. The integral, or the antiderivative rather, of 1 over u du is the natural log of the absolute value of u, and we're going to evaluate that from the natural log of 2 to b. So we're looking at the limit as b goes to infinity of the natural log of infinity minus the natural log of the absolute value of the natural log of 2. Natural log of, I'm sorry, that wouldn't be an infinity yet. This would still be a b. Natural log of b minus the natural log of the natural log of 2. But as we take the limit as b goes to infinity, then we're looking at the natural log of infinity minus the natural log of the natural log of 2. And if we think again about natural log of infinity, that's just going to be infinity. Infinity minus a number is still going to be infinity. So our integral is infinity. So that means the integral diverges. So if the integral diverges, the sum diverges. So that sum does not have an answer. So integral test, just take the integral from your starting value to infinity. If you get an answer, that means your series will converge. We don't know what to, but it'll converge. If you don't get an answer, then you know your series is going to diverge. The next test is going to be the p-series test. And the p-series test is very rarely used on its own. It's usually used within another test, but we'll kind of throw it in here. We will say the sum or from 1 to infinity of 1 over n to the p power is going to converge if and only if p is greater than 1. So if p is less than or equal to 1, that series is going to diverge. So converge if and only if p is greater than 1. It's going to show up, if it shows up by itself, kind of like the geometric one did, where it's not going to be very straightforward. So if we had something like the sum from n equals 1 to infinity of 3 over the square root of n. And you'll be asked to say, does that converge or not? So again, it's not geometric because I don't have a number to an n power. But what we can do is we can kind of mess around with this. We want it to look like 1 over n to some power. So we can take that 3 up top and we can pull that out front and say n equals 1 to infinity of 1 over the square root of n. But just like we know from taking integrals and derivatives, we can rewrite the square root of n as n to the 1/2 power. And since 1/2 is less than 1, we are going to be divergent. So this is a divergent p-series because p is less than 1. So that's going to do it for this video. We will see you in the next one.